So in contrast to the classic setting of the retrieval augment generation, where we always encourage the retrieve the relevant information as much as possible to improve the generation performance. In this work, we study a pretty different KINLG setting as before. So in most of the prior KINLG tasks, they assume sparse gold knowledge. But what if there are too much redundant relevant information? So, and actually this case is very commonly seen. For example, in claim verification, which refers to the task of checking whether the claim is supported or not based on the retrieved evidence. Or in our previous CTS project, we observed retrieving a lot of semantically redundant CTS. So based on these background, we propose a new concept called minimal evidence group that fully supports the claim and with non-redundant evidence as a member of the evidence groups. And the size of the evidence group is minimal. So as a background and related work to, so the classic claim verification tasks usually consists of 3 steps: evidence retrieval, evidence selection, and stance prediction. This is, in fact, an inverse of KNLG, which given the generation output, and then it matches the inputs. Our proposed MEG identification extends the step of extend the steps in classic claim verification on the evidence selection and stance prediction steps. Note that none of the prior works address the redundancy problem within an evidence group. And more importantly, so it is insufficient to simply break the claims into subclaims. Even an atomic subclaim can have partially supporting evidence pieces. Taking a concrete example, person A did not violate any law. To really support this claim, then we have to enumerate every law statement, but each of the statement is only a partial supporting evidence. So in terms of the modeling, previous works all worked on the predicting the single pair of claim and the single evidence. But this setting is problematic when there are partial evidence or there are multiple sets of supporting evidence. To formally define MEG that we propose, we define a claim verification task taking a claim and a list of candidate evidence pieces or sentences as the input. The evidence selection step retrieves all evidence pieces that are relevant to claim, and the stance prediction step predicts whether the selected evidence piece supports claim. We define a set of fully supporting evidence pieces as evidence group. And finally, our minimal evidence group means it's fully supporting the claim. So partially support is insufficient. And the member of the evidence group should be non-redundant in terms of supporting the claim. And finally, the number of the evidence pieces in the evidence group should be minimal. To motivate our approach, first, there's no prior data set nor model available for MEG identification. And we also found that directly prompting the LLMs show poor performance. And further, we can prove that this problem is NP hard. So therefore, we have a cold start problem. And for our proposed approach, we propose an exact solution by taking the bottom-up approach to decompose MEG identification into base problems. We iteratively perform the base problem of classic claim verification and then aggregate the result back to obtain the MEG. The base problem specifically here means predicting whether a candidate set of EPs fully supports, partially supports, or does not support the claim. And note that our proposed approach is an aggregation of the classic claim verification. Therefore, the base case of our approach is identical to the classic claim verification. And this is very different from simply just training a model for direct prediction of MEG. So here's our proposed algorithm. We do a bottom-up brute force approach to iteratively merge partial supporting evidence until we find the MEG. The base model here can be implemented with any reasonable approach, such as prompting LLMs or fine-tuning small language models like T5 model. So therefore, a strong base model of classic claim verification results in a good result in the MEG identification. Again, there are no appropriate prior datasets for our experiment. Therefore, we had to filter and convert classic claim verification dataset to align our MEG identification task. For each of the example and for both of datasets, we have annotations of multiple evidence groups. And we assume the annotated evidence groups by human are already minimal because humans are actually good at it. And in addition, all the claims we use are already atomic claims. We use two datasets, SciFact and WISE. SciFact is a biomedical claim verification, and WISE is a claim verification dataset based on Wikipedia. For the settings, we consider the following three baselines. Direct prediction using the LLM with zero-shot prompting, and classic claim verification. So this is, again, a base case of our approach, which simply takes all the evidence pieces as a single evidence group. In addition to this classic claim verification, we apply removal of pairwise redundancy as a third baseline. And for the evaluation, we measure the metric of exact match and the best soft match, which gives some partial credit to the prediction. And we prioritize the precision at 1 score. So here are the results of our MEG identification. Our proposed approach performs the best, while the directly prompting the LLM performs the worst. And we also found that applying redundancy reduction helps improving the performance over the classic claim verification setting. Next, we want to show the healthiness of MEG as a compact set of RAG retrieval result that is particularly suitable for low computational budget setting, such as on-device computing. So our example task is the inverse task of MEG, called budgeted claim reconstruction, another type of KI-MLG task. The setting is that we consider our previously obtained MEG, and also we compare the union of evidence groups and the first K truncated evidence pieces. Given these results, we found that MEGs are much more compact with more than 45% fewer words achieving similar generation performance. So here are some important discussions. When there's no MEG found, then practically we can still obtain the union of the partial supporting evidence as a byproduct. And the next point is that due to the NP hardness of MEG identification, our exact solution trades off the running time for higher performance. That means given a perfect base model, our MEG identification performance should be also perfect. And there's also a faster approach to compute MEG, such as the classic setting with lower redundancy that we presented before, but this is less accurate. And for the future work, currently our proposed approach is more suitable for high quality dataset annotation, which requires robust solution without strict running time requirements. And future works can use our exact solution proposed to create a larger scale data set and then train a well-performing fast model on that data set. So essentially, the idea is similar to distilling system 2 into system 1, which is essentially distilling logical reasoning into simple reflex.